Assalamualaikum and hi everyone. Today I would like to continue our lesson on chapter 3, which is electric current and direct current circuit. Until now, we have been learned some of the topics for this chapter, which are from subtopic 3.1 until subtopic 3.4. So from now on, I will continue from subtopic 3.5 onwards. Okay, let's start now, class. First, we will look at the subtopic 3.5, the resistors in series and parallel. Okay. Our learning outcomes to derive and determine effective resistance of resistors in series and parallel. First, we will look at the meaning of resistor and what is the resistance. The resistor is the component that hydrants the flow of charge in the circuit, whereas resistance is the property or ability of the material that restricts the flow of electrons or current in the circuit. Okay, the symbol for the resistors in electrical circuit, we have two types of symbol here. The first one here is the symbol for the American standard, or we call it the ANSI standard, stands for American National Standard Institution, and the other one is here is the British standard or DIN standard. So we have two standards for the symbol of resistor. So both standards can be used in our electrical circuit. Okay, derivation of effective resistance. Let's look at the figure 3.10. Okay, we have the circuit for the R1, okay, R2, and R3 that connected in series with the potential difference of voltage supply V. Okay, and then we created the current flows in the circuit here. Okay, when the current flows in the circuit, it will creating the voltage drop or potential difference across each of the resistor, such as for the V1 is the voltage drop across R1, V2 voltage drop across R2, and V2 is voltage drop across R3. The voltage drop also known as potential difference. Okay, so the connection of this circuit, okay, such that all components are connected from end to another to form only one path for electrons to flow through the circuit. One path means it's only one current flows in the circuit. Okay. The same current I flows through each resistor, where we can have the equation here. The total current I equals to I1 equals to I2 equals to I3, where the I1, I2, and I3 is the current flows through the each resistors respectively. The potential difference across each resistor is differs. Okay, so the total potential difference, the V in the circuit, is given by V1 plus V2 plus V3, which is the V1 is the potential difference or voltage drop across the resistor R1, and V2 is the voltage drop or potential difference across R2, and V3 is the potential difference or voltage drop across R3. Okay, then from the definition of Ohm's law, we have the question here. Okay, the V, the total potential difference in the circuit equals to I times R effective. EFF stands for effective. And V1 equals to I R1, V2 equals to I R2, okay, and V3 equals to I R3. Seems the current is the same in this series circuit. By substituting the formula for the V1, V2, V3, and V in the equation 3.11 above, yeah, we will substitute the equation here. Okay, I effective equals to IR1 plus IR2 plus IR3. Okay, and then we will take out the I. Okay, and then the last one will get the equation for the R effective for the series circuit is equals to R1 plus R2 plus R3 and so on. Okay, so this is the equation for the effective resistance that connected in series. Okay, that means we must plus up all of the value for the resistance in the circuit in order to get the effective resistance, or sometimes we call it the total resistance. Right. So figure 3.11 above shows the example for the series circuit. Okay, we have the supply 35 volt here. Okay, the resistor R1 equals to 30 ohm, R2 is equals to 50 ohm, and R3 equals to 60 ohm. So we need to determine or calculate the total resistance in the circuit, current flows in the circuit, and then voltage drop across R2. Right. So how we are going to solve this problem or this question? We need to take out all the information that given in the equations, okay, such as the Vs equal to 35 volts, okay, R1 equals to 30 ohm, R2 equals to 50 ohm, and R3 equals to 60 ohm. Okay, the first one, the total resistance. Okay, total resistance from the derivation of effective resistance just now, we have the equation here, RT equals to R1 plus R2 plus R3. So just substitute the value for the R1, value for the R2, value for the R3 here, right? So then we have the total resistance in the circuit is 140 ohms. Second, we need to determine the current flows in the circuit. We will use the Ohm's law equation. Okay, IT equals to Vs over RT. The Vs value is 35 volt. RT is 140 ohm. So we get the value for the IT, or the total current in the circuit, is 0.25 ampere. Okay, voltage drop across R2. Also, we use the Ohm's law. VR2 equals to IT times R2. The IT is 0.25 times the R2 is 50. So the answer for the VR2 or voltage drop across R2 is 12.5 volt. Now, we make some summary for the resistor in series. Okay, the first one is circuit arrangement. So this is the one kind of circuit arrangement for the series circuit, whereas we have the three resistors that connected in series. Okay, and then equation that involved in this series circuit, and then the other one is characteristics. Okay, let's go to the first one. Okay, in the series circuit, the total resistance in the circuit is just plus up. Okay, like here, R1 plus R2 plus R3. Or you can say that is accumulated resistance is equals to the total resistance in the circuit. Second one, the current flows in the circuit is only one current flows in the circuit. Okay, I equals to I1 equals to I2 equals to I3. That means it's only the same current I flows in the circuit. Okay, the third one, the voltage drop. Voltage drop across R1. Okay, it's not equal with the voltage drop across R2, and it's not equal with the voltage drop R3. So voltage drop across each resistance is different. Okay? Different values of resistor used. If the resistor values is different, so the voltage drop across them is also different. The total voltage or the potential difference in the circuit equals to the voltage drop across R1 plus voltage drop across R2 plus voltage drop across R3. Okay, so the accumulated voltage drops across all resistors is equals with voltage supply. Okay. Then the power. The power dissipation for the R1 is not equal with the power dissipation of R2 and it's not equal with the power dissipation of R3. Right? And the total power dissipation is equals to the power dissipation of R1 plus power dissipation of R2 and plus power dissipation of R3. So that means the accumulated power dissipations of each resistor is equal with total power dissipation in the circuit. So this is some of the summary for the resistors that connected in series. Now we will look into the resistor that connected in parallel. First, we will derive the effective resistance for the resistors in parallel. Consider that we have the circuit, okay, like the figure 3.2a, okay, and then the figure 3.2b here. Okay. If we look at here, okay, the voltage drop across R1, V1, voltage drop across R2, V2, and voltage drop across R3 is V3. But here, we have the current that flows into this junction or this branch, okay, is different, right? So, in this connection, the parallel circuit is the circuit where the connection in which two or more current paths are connected between the two same point. This is the meaning of parallel circuit. Okay. We go further. For the resistors in parallel, the potential difference is the same. Means the voltage across each resistor is the same, where you can write the equation V equals to V1 equals to V2 equals to V3. Okay. Whereas for the current, since the charge is conserved, therefore the total current I is given by equation I equals to I1 plus I2 plus I3. And then from the Ohm's law, we can have the equation the I, the current flows in the circuit, the total current equals to V, the total voltage in the circuit over R effective. Okay. I1 equals to V over R1, I2 equals to V over R2, and I3 equals to V over R3. Since the voltage that drop for each of our resistor is the same here, so we can have this kind of equation. By substituting the value for the current I1, I2, I3, and I in the equation 3.14 above, okay, we can get the equation here V over R EFF or effective equals to V over R1 plus V over R2 plus V over R3. Okay, and then we will take out the V in the formula or rearrange the formula or equation. We will get the final equation for here is 1 over R effective equals to 1 over R1 plus 1 over R2 plus 1 over R3. So now here we will get the equation for the effective resistance when the resistance is connected in parallel circuit. Okay, 1 over R EFF or effective equals to 1 over R1 plus 1 over R2 plus 1 over R3. Okay. We will look at the example. Look at the figure 3.13. Okay, we have the potential difference that's applied to the circuit, 6 volt. Okay, here. And then we have R1, 4 ohm. Okay, R2, 20 ohms. And R3, 20 ohms. And the current that flows through each branch of each junction here, I1 is the current flows to the resistor R1, I2 is the current flows to resistor R2, and I3 is the current that flows through resistor R3. Right? So here we have the total current that flows in the circuit is IT. So we need to determine or calculate the total resistance in the circuit, total current that flows through each resistor, okay, R1, R2, and R3, and power dissipation on R1. Okay, look at the solution. Okay, so we take out all the function that given in the question, such as Vs equals to 6 volt, R1 equals to 4 ohm, R2 equals to 30 ohm, R3 equals to 20 ohm. So the total resistance for the circuits, we use the formula for the effective resistance in the parallel circuit. 1 over RT equals to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, just substitute the number in the equation. Okay, for the R1, R2, R3, okay, we'll get the answer for the total resistance in the circuit or effective resistance in the circuit is 3 ohm. Okay, the second one, determine the total current. We will use the Ohm's law equation where the IT equals to Vs over RT. So Vs is we have 6 volt and RT is 3 ohm. So the answer here for the total current that flows in the circuit is 2 ampere. Remember, this is total current in the circuit, not the branch current. Okay, branch current is I1 or I2 or I3. Okay, now we need to determine the current that flows through R1. So for the current flows through R1, the IR1 or I1 equals to voltage drop across R1 over value of R1. So the voltage drop across R1 is equal to the power supply or voltage supply is 6 over R1 is 4. So the value for the current through R1 is 1.5 ampere. Then current flows through resistor R2 or I2 equals to voltage drop across R2 over value for the resistor R2. So voltage drop is 6 volt. Value for the resistor 2 is 30 ohm. So the answer will be 0.2 ampere. And the last one for the current through resistor R3. The current flows through resistor R3, we note as IR3. So the equation is R3 equals to V over R3. Okay. Now the voltage drop across each resistor is the same. So the value for the V is 6 volt over value for the R3 is 20 ohm. So the answer for this current flows through resistor R3 is 0.3 ampere. The last one, to determine the power dissipation on R1, we use the equation of P equals to I times V. Okay? P of R1 equals to I that flows through resistor R1 times the voltage drop across R1. So equals to 1.5 times 6. The answer will be 9 watt. So this is the power dissipation on the resistor R1. So we have summary for the resistors in parallel. Okay, we have the circuit arrangement such that for each of the resistor it has their own current. Okay, for the current through the resistor R1 is I1. Okay, current through resistor R2 is I2, and current flows through resistor R3 is I3. Sometimes here we call it the branch current. Alright, the equation that involved for this parallel circuit of parallel resistors, okay, 1 over RT or R effective equals to 1 over R1 plus 1 over R2 plus over 1 over R3. Okay, accumulated resistance is smaller than any of the individual resistance. That means the final answer for the R effective must be smaller than any of the individual resistors in the circuit, or must be smaller than the smaller value of resistance in the circuit. Okay, the second one, the current that flows in the parallel circuit I1 is not equal with the I2 and not equal with the I3. That means the current that flows through each of the resistor is different. Okay? Or we can say that different current value flows through each resistor. Okay, then from the current also we can have the equation of I, the total current in the circuit equals to I1 plus I2 plus I3. Okay, then here we become the total current. Accumulated branch current is equal with the total current in the circuit. That means we must plus up all of the current that flows in the branch resistor in order to get the value for the total current. Then the voltage across each resistor in parallel circuits is the same. In terms of equation, we can write V equals to V1 equals to V2 equals to V3. Okay. The voltage drop across each resistor is equal. Okay. Although different values of resistor is used, that means the voltage drop across the parallel circuit is not depending on the value of the resistor, but it depending to the voltage that cross them. Okay, for the power dissipation across resistor R1, the power dissipation for the R2, then power dissipation for the R3 is different. So, in terms of equation, in terms of equation, we can write P1 is not equal to P2 not equals to P3. Okay, that means PT or the total power dissipation in the circuit equals to the power dissipation of R1 plus the power dissipation of R2 plus the power dissipation of R3. Then we can get the value for the total power dissipation. Or we can say that the accumulated power dissipation of each resistor is equals with the total power dissipation in the circuit. So now we already learned about the resistor in series and parallel. Okay, now we will look at the resistors in series and parallel. That means the series and parallel circuit both is embedded in one circuit. Okay. In order to do the analysis for this circuit, okay, we have the analysis technique. Okay, the first one is the goal for the series and parallel circuit is to be able to determine all voltage drops, currents, and power dissipation. Okay, that means when we analyze the circuit, we will be able to determine all those voltages, all those currents, and all those power dissipation in the circuit. The general strategy to accomplish this goal is as follows. Okay, first one, we will assess all of the resistors that are connected in simple series of parallel circuit, and then we analyze them. We draw the circuit by replacing each of series of parallel circuit or parallel resistor combination with the equivalent value of resistor. Okay, step number 3, we must repeat step 1 and step 2 until the entire circuit is reduced to one equivalent resistor. We call it, this one is the simplification of the circuit. Okay, and then number 4, calculate the total current, okay, from the total voltage and the total resistance of the circuit. Right, this is the way how we are going to analyze the resistor that connected in series and parallel. Okay, example for this circuit, for the figure 3.14, okay, we have combination of those series and parallel in one circuit. Okay, now for this circuit, I will analyze by using 1, 2, 3, 4 steps. Okay, step number 1, okay, to equalize the resistor for the circuit of number 1 here. See the green here. Okay. So since the R, now R number 1, R1 is 4 ohm, R2 is 2 ohm, okay. R3 is 1 ohm, R4 5 ohm, R5 3 ohms, R6 6 ohms, and R7 8 ohms. Okay. So look at the first one. Okay. The resistor 1 ohm or R2 and R3 here. Okay. So we will examine here. Since this is the two resistors connected in series, so we will plus up this one. So R34, sorry, it's not R2 and R3, but R3 and 4. So R3 and 4 is connected in series. So the total resistance is R3 plus R4. So when we put the number here, 1 plus 5 will be 6 ohms. Okay, and then step number 2 here for the blue color here. Okay, because this is the parallel circuit, we need to analyze them first after resistor R3 and resistor R4. Alright, so here is the connected in series for the resistor of R5 and 6. So the effective resistance for the R5 and 6, 1 over R5 and 6 equals to 1 over 3 for the resistor 5 and 6 for the resistor 6. So there will be the R5 equals to 2.0 ohm. Okay, and then 6. And then we look at here. So the second step, second one, the blue one. Okay, and so the first one is now the first one. Okay. And then for the R 256, we must plus up the value for the resistor R2 here, 2 ohm, okay, with the R56, okay, with the R56, okay. So here the third step is here, okay, plus up here. So 2 plus here is 2, here will be reaction to the resistor R56. Here is 2 ohm, 2. Right. Then the third step, okay, determine the value for the resistors that connected in series and parallel for the resistor R2, 3, 4, 5, 6. Okay, R2, 3, 4, 5, 6. Now, 1, 2, 3, 4, 5. So this connection now will be in the parallel. So we have the equation here, 1 over R effective equals to 1 over R3 and 4 plus 1 over R for the resistor 2, 5 and 6. So we will put in the equation here, 1 over 6 plus 1 over 4. So the answer will be 2.4 ohm. This is the effective resistance for the resistor that connected in series and parallel for the R2, 3, 4, 5, 6. Now, this is the third step. And the last one, the first step, for the final step, R equivalent, okay, equals to, since the R1 with the R of 2, 3, 4, 5, 6, and also for the R7 is already in the series circuit. So we can put the number equation in the series circuit. So it will be R1 equals to 4 plus R2, 3, 4, 5, 6 is 2.4 ohms plus R7 here is 8 ohm. So it will be the final answer 14.4 ohm. Okay, here I put it at the bottom here. So here will be the 4. Okay. So it's the R2, 3, 4, 5 and 6. 5 and 6. And then here is the for R1 actually here. And here is for the R7. Okay. So here is the R equivalent or R defective. Okay, now the final answer for the effective resistance or R equivalent for this circuit is 14.4 ohms. Now we have another question here. For example, 3.10. Okay, for the figure 3.15. For the circuit in figure 3.15, calculate the effective resistance of the circuit. B, the current passed through the 12 ohm resistor. And C is the potential difference across 4.0 ohm resistor. D, the power delivered by the battery. And the internal resistance of the battery may be, we ignore the internal resistance of the battery. So how we are going to solve this question? Okay, look at the solution here. Okay, we need to simplify the circuit. Okay, from the more complex circuit to the more simplified circuit. Okay, here R1 and R2 is connected in series, so we transform to here for the R12. Okay, so it will be R12 with the resistor R3 connected in parallel. Okay, whereas for the R1 and R2 connected in series. Okay, now R12 equals to R1 plus R2 only. Just put number in the equation. We get the value for the R12 equals to 16 ohm. And then resistor R12 and resistor R3 are connected in parallel. So therefore, effective resistance for this circuit is 1 over R effective equals to 1 over R12 plus 1 over R3. So the final answer for the effective resistance for the circuit is 1.78 ohm. Okay, B, you need to determine the value for the current flows in the circuit for the I2. Okay, since the R12 and R3 are in parallel, so the voltage drop across them is equal. So V voltage drop across resistor R1 and R2 equals to voltage drop across R3 equals to V equals to 8 volt. Since this is connected in parallel. So therefore, the current that's passed through resistor R2 is given by the equation I2 equals to V voltage drop across R1 and R2 over resistor 1 and 2. This combination of the resistor, right? Okay, so we have the answer here. The I2 equals to 0.5 ampere. C, you need to bring the voltage drop across resistor R1. Okay, since the current in this circuit is the same, I1 equals to I2 equals to 0.5 ampere, then hence the potential difference across R1 okay, is V1 equals to I1 times R1. V1 equals to I1, let's substitute the I1 0.5 ampere, and then R1 is 4 ohm. So the voltage drop across resistor R1 is 2.0 volts. About the power delivered by the battery, we will use the equation of P equals to V square over R effective. So this is one of the equations that used to determine the power in the circuit. And just substitute the number in the equation for the V8 volts square over R effective 1.78 ohms. So the final answer for the power delivered by the battery is 36.0 watt. Okay, so now we have two examples for the circuit just now. We have another one example 3.1 here. Okay, for the figure 3.16, we need to calculate the effective resistance between the point A and B. Okay, between point A and B, we need to determine the R effective. Right. So look at the connection of the circuit. Okay, we have the both series and parallel circuit that combine in one circuit. We call it the series and parallel circuit. Okay, so the solution for this circuit, we need to simplify the circuit to become only one resistance, which is effective resistance in the circuit. Okay, here, the complex circuit here, we must transform to the circuit, the simple one, R effective. Okay, here is the effective resistance that we need to determine. Okay, look at the one by one, the process how to simplify the circuit. Okay, look at the R1 and R2. R1 and R2 are connected in series. So the R12 equals to R1 plus R2 only. Okay, just put the value for the R1 and R2 here in the equations. Okay, so we have 5 plus 5 equals to 10 ohm. Okay, then this the resistor R12 here, okay, is connected to the R3 by parallel circuit. So thus for the R13 must be used the equation for the parallel, which is the 1 over R1 to 3 equals to 1 over R12 plus 1 over R3. Okay. Now our final answer for the resistor R1, R2, and R3 is 5 ohm. Okay. Then resistor R1, 2, 3 after we simplify here, right, is connected in series with resistor R1, 2, 3, 4. Okay, so thus R1, 2, 4 is given by equation R1, 2, 3 plus R4. Okay, R1, 2, 3 here plus R4. Okay, just substitute number or value for the R in the equation. R13 is 5, R4 is 20. So the final answer for the R1, 2, 3, 4 is 25 ohm. Okay, then we put the value for the R1, 2, 3 in the circuit there. So you can see that the resistor R1, 2, 3, 4 and the resistor 5 is connected in parallel. So we will use the equation for the parallel circuit. So now the final answer for the resistance effective in the circuit or effective resistance in the circuit is 1 over Rf equals to 1 over R1, 2, 3, 4 plus 1 over R5. Substitute the number in the equation, we get the R effective for this circuit equals to 7.14 ohm. Okay, the final answer for the effective resistance in the circuit is 7.14 ohm. Hopefully, the class will understand much about this topics. Until then, thank you very much. See you again for the next chapter. All the best. Thank you very much.